asbestos suit. Okay, so I think the reason why I got interested in deep learning, and this is not just over the last 5-6 years, but probably the last 25 years since I got involved in machine learning, pretty much. I've been interested in feature learning, and deep learning is really about feature learning. And I think we have a good handle on how to train classifiers nowadays. But much of the work of figuring out feature sets, kernel functions, things like this, metrics, is still up to a lot of sort of handcrafting and engineering. And it's something that a lot of theorists kind of sweep under the rug because they consider that someone else's job. And a lot of machine learning people also consider that someone else's job. But I think it should be our job as machine learning people to really figure out how to come up with good features, perhaps from data automatically. And I think it's really the next challenge of machine learning. If you want to kind of make some significant progress towards applying machine learning to a wider set of projects, if you want to be able to handle lots of different data sets without spending a lot of human labor designing feature sets, we have to be able to learn features. And that's all what deep learning is about. But if you're talking about learning features, you're talking about learning representations of the perceptual world. And it's a very complicated problem. We can't get around that. It's not just a problem for machine learning, it's a problem for biologists, neuroscientists who want to figure out how the brain works, for a lot of people in application areas such as vision, signal processing, speech, etc. So, the normal way to do pattern recognition is you have your uncrafted feature extractor, you plug your favorite classifier on top, turn the crank, and you're done. But in fact, that model is not used so much anymore in computer vision, for example, or even in speech recognition. The model is more like 3 blocks. I'm talking about mainstream models, not sort of the latest deep learning kind of approaches. The first layer is generally handcrafted. So in the case of speech recognition, it would be things like MFCC, constant Q transform, things like that. In the case of vision, it would be SIFT and HOG features and various other acronyms of the same type. And then there would be a second stage, which sort of extracts mid-level features, if you want. And that second stage usually is based on unsupervised learning. Very simple things like k-means or sparse coding. Mixture of Gaussians, which is basically k-means with soft assign. And this serves the purpose of taking sort of group of those features and embedding them in a high-dimensional space in a nonlinear way, so that a classifier on top will have a better chance of kind of classifying this with linear separation. So if you think about a speech recognition system, you have MFCC here, you have mixture of Gaussians, which basically represent a segment of audio into a very large sparse vector, which consists of the response of the Gaussians to each of the acoustic input features, and then the classifier is kind of a linear combination that gives you a classification over phonemes or phones, or states in the HMM if you stick a structure prediction system on top of it. For computer vision, you would have dense SIFT extracted over the image, and then a second stage consisting of sort of expanding the SIFT vectors into a high-dimensional representation using k-means pooled over areas, what people in computer vision call bag of visual words, which neural net people call pooling. And then you stick that into a classifier. Doesn't matter what it is, really. But what we'd like to replace this by is essentially a kind of a cascade of transforms, each of which is trainable, that turns the kind of low-level representation into a slightly higher-level representation. And by cascading those things, we get to sort of a good enough representation that captures the dependency in the data. So, for example, for images, you might imagine extracting things like oriented edges, and there's a number of unsupervised learning algorithms that naturally, when you train them on natural image patches, just come up with edge extractors. In fact, almost all of them do. And then you could imagine the second layer coming up with sort of detectors of motifs, and then the third layer into parts of objects, the fourth layer into objects, and etc. And that would kind of jibe pretty well with what we know about the visual cortex, for example, where we know that the process is hierarchical. There's kind of a number of areas, well-identified area in the brain where the signal goes through, and it's, there's maybe 5 or 6 of them. It's a very fast process. Now, here's the first theoretician dilemma, which is that people in machine learning like kernel machines very much, and you kind of parameterize your family of function as a linear combination of the application of a kernel function to your input vector matched with one of the training samples, k of xxi, where xi is one of the training samples, and then you linearly combine them with weights alpha i's, and that's a kernel machine. And you can pretty much approximate anything you want on any training set with a function like this if you appropriately choose the k function. The problem, of course, is that doesn't scale very well when you increase the number of training samples to very, very large numbers. And then you have to decide what the kernel function really should be. And that's actually not a trivial problem at all. And you can get into issues training SVMs where it's essentially intractable if you have more than a couple 100,000 training samples, if the dimension is too high, if the kernel function doesn't make sense for the data you're looking at. So that's basically...
Has any prediction ever
made which argument?
That we can just go with a 2-level structure?
Yeah, Vatnik.
For this reason?
Well, I mean, basically, everybody who is completely enamored with kernels, I mean, not everybody, but a lot of people, Vatnik is the first one of them. Vatnik was in my group,
and he makes an argument?
He doesn't understand the usefulness of deep learning at all, no.
No, that's a different thing.
Well, but it's for that reason.
It requires exponentially many...
But it's essentially for that reason. So it's, yeah, I mean, the question is that, of course, you can require, for most functions you want to compute, you require an exponential number of those terms in the sum. Unless you have a particularly well-designed kernel that solves the problem, but then, you've swept the problem under the rug.
I think he believed that there was some kernel out there which worked very well on all kinds of problems.
On everything?
Unrealized problems.
I just don't believe this at all. Do you?
But anyway, I'm just saying that's a strong, I'm sure nobody said that.
Yeah, maybe it's a bit of a, exaggeration. So, for people who have studied circuit complexity theory, and I know almost nothing about this, certainly much less than a whole bunch of you guys here in the audience, Sanjeev among them. There's those arguments that certain functions require a certain number of layers of nonlinearities, of nonlinear operations, if you want to be able to compute the function with a polynomial or less than exponential number of parts. Okay, and so that's kind of one hand-wavy justification for why you need deep architecture, simply because if you allow circuits to be deeper, you can gain a huge factor in their overall size, perhaps an exponential factor in their overall size. So it's basically trading breadth for depth. You build a circuit, you can always build it with 2 layers, with ands and ors, conjunctive normal form, disjunctive normal form. But if you use more layers, it'll be much smaller, it'll take longer. Best example is things like parity or addition of the numbers, which are linear in number of bits, or logarithmic in number of bits if you design it right with Boolean functions. But they're very complicated if you impose the 2-layer architecture. Right, so here's a couple more nightmares for theorists about deep learning. The first one is that deep learning involves minimizing non-convex loss functions. So if you have a deep architecture and multiple nonlinearities in the system and parameters at multiple levels, then your loss function is going to be non-convex whether you like it or not, at least in the original space in which the problem is formulated. Of course, we could come up with, splitting layers and with latent variables and sort of embed this into a higher dimensional space where things might be a little more well behaved. And there are sort of attempts at doing this, but the sort of, canonical formulation is really non-convex.
But that again is a straw man, right? Because I'm being contrary to the contrary. Because again, like everybody today that they're talking, these are all non-convex problems. The point is, eigenvalues and all these other things.
Yeah, but eigenvalues is a well-understood non-convex problem.
Fine. What I'm saying is they showed that, that you can use it to make progress.
Sure, right, absolutely. No, I mean, the inference problems are usually non-convex. But for some reason, there is a bit of a fixation from the machine learning community on the fact that the learning part of it, not the inference part, but the learning part of it has to be convex. And I just don't understand that.
I will,
Michael.
I mean, to be a bit of a contrarian too. we found that we can learn robustly in very, very high dimensions. And you might say, so in LP, we had engineered features a lot. But in reality, we just throw in an awful lot of features, typically trigrams, bigrams, a lot of low-level features, and
Sure.
then linear classifiers in those high-dimensional spaces.
Yeah, but sure. But then the best language models have the lowest perplexity records at the moment are deep learning systems, where with a huge number of features. So I mean, there's a bit of a race between.
We throw in features, then the convex optimization does feature selection in a sense. So.
Right. So sure. I mean, you have an approach of kind of having your sort of boutique designer features, and have a kind of a minimal set that solves your problem. You can have a huge number of features and sort of rely on your learning algorithm to select the right ones.
They're typically a few atomic features and higher order polynomials. So there's 3, 2, 3, 4. I mean, essentially we're learning linear classifiers in explicit polynomial spaces.
So you're saying, there's no point learning features. We just take the whatever raw feature we're given, we sort of generate combinations of them more or less.
I think speech and vision are different actually from language.
So I don't think so. I think they're really the same nature. But okay.
So what about
Oops.
intelligence? You mentioned,
Yes.
you mentioned all these features are used for images, like
Uh-huh.
script and so on. How well do deep learning methods use?
So okay, so there's a number of different benchmarks in computer vision. There's one, there's the Pascal competition organized in Europe every year. This year is the last one actually. And there are several sub-problems. There are problems where the training set is relatively small, which is the traditional kind of normal Pascal competition. And for those, the techniques that work the best are techniques that use an enormous number of features and then some sort of multiple kernel learning technique of some kind, some sort of way of doing feature selection. And then a kind of, fairly simple structure prediction model on top of it for movable parts and things like that. So it's a bit like, it's going to have one more layer maybe on the model that I showed, and it's, a large number of features. But there is another problem called ImageNet where there the number of training samples is much larger. The problem has many, many more categories, and there the record holders are deep learning systems. It's very recent, over the last month or two, but it's.
By the way, simple comment. So it seems like the straw man here is not theoretician, but theoretician in the Botanic School. Is that?
Well.
Because I'm reading the rest of it.
Yeah, maybe a little bit. No, I mean, these are challenges. These are not necessarily critique of all theoreticians, of course, but these are sort of interesting challenges, including for people within the machine learning community. I tell you, this is not. I'm not making this up. There is a whole bunch of people within machine learning who are completely scared of non-convex problems and will not touch them, and partly because of the fact that you can prove many things about them, right? So.
So do you think deep learning is successful because of its non-linearities, or, for example, if you think about feature learning HMMs or LGA, you can think of those as methods for inducing features.
So the only place within an HMM where you induce features is when you place in speech recognition, for example, you have a mixture of Gaussian model. Placing the Gaussians, it's kind of like learning features, mid-level features.
It's learning to live like variables, right? And if you want to be deep, you can also stack those. But it's kind of doing. I'm just trying to understand that. When you have deep learning nowadays, and that's stuff like sigmoids, do you think that's critical for?
No, not at all. No, I'm not making this assumption at all. Okay, I'm just saying you need nonlinearities and you need multiple layers of them. Now, what nonlinearities to use, that's kind of up to you a little bit, or up to the problem. I'm not insisting that it should be sigmoids on linear combinations. No. Right. So, as an example, every practical speech recognition system uses non-convex optimization, and it's true for handwriting recognition systems also, the practical ones. But somehow not true of a lot of things that are treated in machine learning. So I don't want to get into things that are a little too sort of hand-wavy, but it's clear that things like human learning is not convex. If it were, then the order in which we learn things wouldn't matter, and it obviously matters. So what that means is that if our environment creates a loss function for us, it doesn't have a single minimum because we get to a different one depending on the order in which we learn things. So much of deep learning doesn't really have specific generalization bounds. So you can apply VC theory to anything that has a finite VC dimension, and all those results apply to anything, including deep learning systems. And as far as I'm concerned, that's all I need. And the reason that's all I need is because I've never seen an example where a generalization bound was useful in practice. It's conceptually very interesting. I think it's very nice that people work on them. I had people in my group work on them at AT&T. It's not like it's something that we should stop working on, but we should keep in mind that they essentially have no practical applications. Okay, everybody who works in practice and does model selection never use any formula like this. They use cross-validation, and it's 100% cross-validation. Yes.
I just want to point out that the VC theory underwent the same problem that it was explaining neural nets in the end of the 90s. And there came analysis like random marker complexity analysis and more sophisticated techniques. We do give you insight about what's important.
Right.
Margin theory that shows that it's not the number of layers that's important from a statistical point of view, not computational.
So,
but the size of the weights, for instance.
right. So that's only relevant for linear systems. If you have a multi-layer nonlinear system, the size of the weights really.
So anytime you have nonlinearity, which is Lipschitz.
Oh, right. Okay. Sure.
Then it works for that.
Sure.
If you have nonlinearities, which is functions.
No, usually they tend to be
And this theory is exactly
a little smoother than that. I mean, you can come up with any regularizer you want. I don't think there's anything magical about margin maximization, frankly. I think it's just a convenient way of kind of, reformulating, weight decay. But
So I'm not talking about maximizing margin, but as explanation for why
right,
these neural nets work well in practice.
right. Yeah, I'm not sure I'm entirely convinced of that. The empirical evidence does not really agree with that. I mean, you can train ridiculously large. So that's something that we didn't realize 15, 20 years ago, which is that you can train ridiculously large neural nets, even without much regularization, and they will actually work pretty well. And we don't know why. Yes? Fact-based? Yeah, I mean,
There's a pretty large pool around the current space where the training error is more or less.
right,
It's low, not entire volume, related volume.
right.
That to me is one very nice explanation.
There are, some hints, from different angles. But the point is, none of those results actually have any kind of practical consequences, really. As long as there is a bound, is finite VC dimension, I'm happy. Right. Okay, but it's a bit of a theoretician paradise too, because of all those challenges that are unresolved, and so there's a lot of work to be done. And things like, what's the geometry of natural signals in high dimension? So, Sanjeev's talk this morning assumed uniform distribution over the unit cube. But natural data is never like that. In fact, all the algorithms kind of try to exploit the fact that it's never like that. Other questions, is there equivalent statistical learning theory for unsupervised learning? I'll come to that maybe if I have time. What good criteria are there for unsupervised learning that, for which we can say things? So you can also view deep learning as kind of a special kind of factor graph with latent variables, where latent variables could be the hidden units. The point was made just earlier, and then you can sort of fold this back into the machinery of factor graphs and graphical model and inference algorithms of the type that David was talking about, except here we're in continuous space, so you can't really use this trick of kind of the product. You have to be in a Hilbert space, but that's okay. And then there is a lot of really sort of interesting work around the properties of particular deep architectures. There's very interesting work by Mala. So this is more connected with continuous math rather than sort of the theoretical computer science. It's more connected with harmonic analysis than anything else. And then a lot of work on kind of techniques like sparse coding, which are some of the most popular techniques for feature learning. And there's a big connection with applied mathematics, the world of applied mathematics there. So the thing about deep learning today now is that people are starting to get interested in it because it's beating records in a number of different areas. So in speech recognition today, deep learning is the hottest topic. Everybody's talking about it, and everybody's working on it, and everybody's putting resources into it because a few long-standing records have been beaten, and pretty badly, by deep learning techniques. And the latest speech recognizers that Microsoft and Google have deployed for their various mobile applications and things like this are all based on deep learning now. So, so that is a very short time between sort of research and commercial applications, essentially.
So is it the primary underlying engine?
Yeah. The primary underlying engine of the speech recognition system used in the latest version of Android is deep learning. Yeah. It's not a mixture of Gaussians anymore.
Sorry?
It's not a mixture of Gaussians anymore for acoustic modeling. It's a deep learning system.
But deep learning is this exponential size mixture, at least RBM.
So this is not based on RBM. This is basically a backprop net with it's backprop network, but it's pre-trained unsupervised. I mean, they don't give us the detail. They don't tell us the details of how they do it, but that's what we can infer somehow. It's about to become a really hot topic in computer vision. There's a lot more resistance in computer vision because there's a lot of vested interest in sort of feature design. That's bread and butter for a lot of people in computer vision. And so since deep learning attempts to displace that, there's more resistance. But it still is very popular. There was a tutorial at the last CVPR that was extremely well attended. A bit of that might be happening in NLP. I'm not sure. I don't want to say too much here because the people here are more involved in NLP much more than I am. And there's a big interest from the applied math community in the kind of questions that are related to this. Okay, so one question we can ask ourselves is what do we put in the box I was kind of mentioning before? And one of the basic building blocks that people have converged towards for building deep learning system is something of that nature. So I'm talking about feed-forward system. There is occasionally some unsupervised learning with sort of feedback systems like RBMs, which I'll talk about later. But in the end, the system that's used generally is feed-forward. And the sequence of operations is the following. First, there is some sort of normalization. You can think of this as contrast normalization, rotation of the variable to make them decorrelated. So whitening, for example, ZCA would be a good example of what you would do, what you would put in this box. Second stage is a filter bank or linear transform. So in the case of images, it would be filter banks because you need the linear transform to be convolutional. But in the general case, it's just a matrix. And it's a matrix where the number of rows might be larger than the number of columns so that the dimension is expanded from the input. We're not talking about dimensional T-reduction here. Then there is a nonlinear operation, which may not be a point-wise nonlinear operation. It could be something very harsh, like zeroing out some components, shrinking, winner-take-all, some competition mechanism. Or maybe a simple sigmoid if you want to stick with classical neural nets. And then some sort of feature pooling, so something that takes the individual features, a group of them, and aggregates them with an operation like average or log of some of the exponentials or max or min or something of that type. Any kind of symmetric aggregation function. And the role of this is to build invariance and smoothness of the representation with respect to transformations of the input. And the cool thing is you can stack multiple stages of this, and you know, if you believe in gradient descent, you can train the whole thing with gradient descent in supervised mode, and that actually works pretty well. It depends on what precise architecture you put in, but it works pretty well.
And there are multiple levels of this feature.
Right, so each of these macro blocks is a stage, right? And you can have 2 or 3 or 4 stages of that, right? And one stage has essentially one level of harsh nonlinearity in it. One level of harsh nonlinearity in it, okay? The nonlinear box right there.
Like this RBM or whatever.
Well, so RBM would be some sort of threshold function, probabilistic threshold function, but you know, it could be sigmoid, winner take all, you know, sparse coding, something like that.
You said you could train this
With backprop. Yeah, that works just fine. Again, it depends on the architecture and depends. So if you use an architecture like on convolutional net, which I've been using for a very long time, which basically is built around this kind of succession of modules, there is no problem of symmetry in that system, and that turns out to be very easily trainable with gradient descent, and it works just fine. So in fact, some of the best results on ImageNet were obtained with very vanilla convolutional nets, you know, trained on fast GPUs with various tricks, and those results are out of Jeff Hinton's lab, and Google also has some similar results. Yeah.
At every stage, potentially, if your parameters are bad, you could lose a lot of information.
Yeah.
So, what's the principle behind ensuring that when you collect these features and try to trim down to a lower dimension space, you do not?
It's not low dimension. It might be high dimension, right? So the
Higher than the input?
Yeah, definitely higher. Yeah. Or not sparse, but you know, here we're starting from an image, and here we have 20 images of the same size. That's our feature or first level feature representation. So there's an expansion of 20 to 1. Okay, and then
in what sense are you recognizing feature?
okay, so the only place where you have a reduction of dimension is the pooling operation. Okay.
At the end of stage 1, you sort of have a compressed.
No, because the filter bank has expanded, and so it's quite possible that the pooling will not reduce by the same ratio as the expansion, and so the proper architecture usually for deep learning system is the first few intermediate layers are much higher dimension than the input. And if you think about what supervector machine does, right? Supervector machine is a 2-layer system where the first layer has a dimension, number of hidden units, if you will, whose size is the number of support vectors or the number of training samples if you don't do you know, elimination of weights. So you could think of this as a sparse encoding. If you use an RBF kernel, for example, what you get is a very sparse representation of your input in very high dimensional space. It's not the high dimensional space that people think of when they talk about the kernel trick, right? It's just the dimension is just the number of support vectors. And then it's a linear combination. So you expand into a high dimensional space, and then you can apply linear classifier in the high dimensional space, because in high dimensional spaces things are more easily have a bigger chance of being linearly separable.
So I was under the impression that all these very long chains are hard to train. So I mean, you have to do pre-training and unsupervised.
Right. So
you're saying that's not the case?
I'm saying that's not the case for convolutional net. It is the case for fully connected network where you don't have any structure, but for convolutional net, it's just not so much of a problem.
So convolutional, this applies to images?
So no, it applies to any data where the data comes to you in the form of an array in 1D, 2D, 3D, 4D. Okay, so audio signal, speech in time frequency representation or music, images, video, volumetric images, things like this, right? They all come into an array. And the characteristic that a convolutional net will exploit are the two hypotheses you have to make. One is that the statistics of the signal is invariant to location. Okay, that's true for images. And the second one is that yes. And the second one is that local local patches of variables are highly correlated and are more correlated than faraway ones, right? So that's true for images as well. You know, neighboring pixels are highly correlated, but far away they're not, or less. And so the convolutional net architecture exploits those two things essentially. Right. So this is one that is very old. It's from the early 90s, and this was trained entirely supervised. It's sort of a classical neural net, convolutional net with sigmoids and linear combinations. But the reason I'm showing you this is that if you look at a particular pixel, I don't have a pointer, but if you look at a particular pixel on the input, there are a few pixels that go from white to black to white as the number is being translated. And what that means is that the curve that's being followed in pixel space by the translated 3 is a very highly nonlinear curvy surface. Okay, and if I were to distort this 3 in various different ways, I would get a surface, and that surface will have a high curvature. If I make a similar surface for number 8, for example, which has many pixels in common with 3, it would be another very highly curved surface, and it would be completely entangled with the surface for the 3. It wouldn't touch because there's no 8 that looked like a 3, but it would be completely entangled with each other, and you can't separate them with a linear classifier. So this is the first layer after the first nonlinearity. This is after pooling, and then there's the second linear combination nonlinearity after pooling, and then a third layer of nonlinearity and linear and nonlinear operation. And you hardly see any variable here that blinks from white to black to white or vice versa. There is maybe one of them, but they all kind of go from more gray to less gray, or the other way around. And what that means is that in that space, the manifold of variations of the shape is flatter, and therefore they're easier to separate from each other for different categories.
So it seems like all the action is happening in the last layer, because up until the last one we still have this moving around.
Right. So if you look, every variable in the last layer is essentially influenced by a fairly large portion of the input, a 32 by 32 window on the input, which contains an entire character. And so you can take one vertical slice of this, and that will essentially represent the entire 32 by 32 window. You can think of it as a... Now here's something funny, which is that the mainstream approaches to object recognition in computer vision are actually built on the same model. And they've been arriving at this maybe 5-6 years ago, from a completely different angle, but with some inspiration from convolutional nets and stuff like that, but it's or from biology for that matter. But it's essentially the same architecture. So there's a very popular framework or pipeline which is derived from Lana Lezevnik's paper from CVPR 2006, which he calls pyramid match kernel supervector machine. And the first layer is a SIFT extractor, and we think when you look inside of a SIFT extractor and you figure out what it does is filtering nonlinearity and pooling. Okay, and it's followed by normalization, which I didn't put here in the thing. This is not a critique of SIFT at all. It's actually, I think, very interesting to see that that's the case. But SIFT was actually inspired by biology in the first place. David Lowe says that much himself. And it's inspired by the same biological, neuroscience papers that inspired neural nets, convolutional nets. It's the idea that the feature pooling operation is really crucial to sort of having local invariance to transformations. When you look at what the second stage is doing, generally it's trained by k-means, so there's a bunch of prototypes and then a winner-take-all. And k-means, if you think about what k-means does to an input vector, it turns it into a very large vector with all zeros and 1, 1, where the 1 is located at the index of the prototype that the input is closest to. Okay, and then you take all of those place vectors, which people call visual words. You average them out over an area, perhaps the whole image. That gives you a bag of visual words, and you stick that to a classifier. You can have local bags, concatenate that, feed that to an SVM or logistic regression, and that works pretty well. So it's pretty much the same architecture everyone's using. Well, I mean, sometimes there's a sort of mildly nonlinear kernel, but very often it makes no difference.
So one difference is that this system was partly put together, for example, SIP,
yeah.
by having data sets trained on each part of this was basically training some of the...
No. So SIFT is built by hand. There's no training there whatsoever. Okay?
Well, you could call the cross-validation that they did.
Well, okay, the parameters are adjusted so that it works best on whatever data set. Yes, that's true.
My point is something different, is that your system is entirely trained end-to-end, right?
Right.
Is there any point and any way to actually insert, if you have some amount of ground truth that would be relevant for these intermediate features, is there a way to do that in a framework?
Well, yes, if you have good idea for what the intermediate concept should be, then you might as well train your layer to produce them. But usually, to come up with those, you have to make assumptions that turn out not to be true 100% of the time, and so that limits your performance. So, right. So the interesting aspect of this is that the first stage is fixed, the second stage is unsupervised, the last stage is supervised. That's basically what those mainstream systems are built on. So you can use convolutional nets, train end-to-end with backprop on various applications and beat the record, and it's used commercially in all kinds of stuff. But the latest application that we've used this for is for scene parsing. It's a bit of a complicated convolutional net, which I'm not going to go into. I'm just going to show you the... let's just say that this is a record-breaking application. We have the best known results on 3 benchmarks. I just flashed the result here. So scene parsing is the problem of labeling every pixel in an image with the category of the object that it belongs to. So, yeah, right. So, you have an image and you're supposed to label every single pixel, grass, tree, mountain, sky. So David had a slide that described that problem as well. And the traditional approaches to this are based on fairly simple local classifiers that are trained supervised. So there's a set of images that are fully labeled that you can use for training local classifier that take a relatively small window of the image and then produce an answer. And then the problem is, of course, you have to make those decisions globally consistent, and you use a graphical model on top of that. The option that we've taken with the convolutional net here is to take a very, very large input context window for every decision we make. So every pixel that we classify actually takes a 46 by 46 window at high resolution, another 46 by 46 window at half resolution, which corresponds to 92 by 92 window on the original image, and then yet another one at quarter resolution, which corresponds to practically 200 pixels on the side on the image. And so every pixel-wise decision is using this huge window to make that decision. So if it's tried to figure out if this is a pixel for the head of a person, it will see the entire body of the person and the background and everything. And what that allows us to do is use very simple, methods to kind of make consistent decisions over regions, essentially a superpixel averaging. I'm not going to go to the details of this, but that allows us to essentially beat the state of the art, at least in what's called a class accuracy measure. There's another measure which is pixel by pixel accuracy, which is less interesting. And we also beat the state of the art by a factor of 100 in speed on conventional hardware for this 3 data sets. Because we don't have to do any complicated inference in a complicated graphical model. So that's interesting, fairly recent result. This is a system running on a video here for sort of panoramic video from a guy in my lab wearing a helmet with all the cameras on top of it. And so here each frame is labeled independently of every other frame. So there's no temporal consistency or anything like that. And it makes some stupid mistakes, like very often the road is classified as sand or beach. This is Washington Square Park. There's no sand as far as I can tell, but it does a decent job, and it's as good as it gets for systems of this type today.
So you said there's no inference done at the alpha layer, so adjacent pixels.
So there is. It's based on superpixel. So we do a superpixel clustering. So we get regions that are relatively uniform in terms of color, and the boundaries are lined up with the boundary of the image. And within one of those superpixel, we take the winning majority category or the neural net gives for all the pixels in that superpixel.
So the superpixels happen after the neural net?
In parallel, yeah. right? And they're just based on RGB. No.
So presumably you could have added some temporal consistency.
Yes.
But it didn't help.
Yes. No, it does help. I mean, it helps somewhat. So it helps, but it also makes the mistakes more problematic, right? So maybe that's a better example. So for example, here the buildings in the back are washed out because the lighting is bad, so they're all classified as sky, but then as soon as the lighting changes, they come back to being buildings again. So the big progress over the last few years for deep learning or neural nets is this idea of using unsupervised pre-training. And you know, every group has their favorite methods. You know, Jeff Hinton likes RBMs. Yoshua Bengio likes contracting autoencoder and denosing autoencoders. I like sparse autoencoders. Andrew Ng likes a whole bunch of different stuff, including sparse autoencoders. So, you know, we all kind of try to see what we can do with some ideas. But I'm going to talk about sparse coding. So sparse coding is a way of turning a low-dimensional vector into a high-dimensional one, if you want. But it's going to be a sparse vector. Among all the possible ways of mapping low-dimensional vectors to high-dimensional vectors, we're going to choose a set of high-dimensional vectors that happen to be sparse. So have lots of zeros in it. And the way we do this, so assuming we have what's called a dictionary matrix, by which we multiply the code, the feature vector z, we're going to find this vector z that minimizes the energy function written at the top. And it is the sum of two terms. One is the square reconstruction error. So it's the square distance between the input and the reconstruction, which is the product of the dictionary matrix by the feature vector. And the second term is a penalty term that tries to make the feature vector sparse by just computing the L1 norm of that vector, the sum of the absolute values of the components. Okay? So if you have WD, I give you a Y, you minimize this energy function, and out will come out a Z that is sparse and from which you can reconstruct the input. Okay? Sparse coding. Now it turns out you can learn the WD matrix very easily, just using stochastic gradient descent. And people call that sparse modeling. And that dates back from Osazen and Field in the late 90s, who were neuroscientists. And we came up with this learning algorithm. And if you apply this to natural image patches, what you'll see is that the columns of WD, which are the things you linearly combine to reconstruct input patches, end up being Gabor filters, so oriented edge kind of things. So I've kind of written this as a factor graph. You have variables that are circles, you know, those purple circles. Deterministic functions, so this funny kind of factor graph. I need to be able to represent deterministic functions. So there are those kind of weird-shaped blue things, and then the factors are red, and we're working in a log domain, so things are additive and not multiplicative, even though they're called factors. Right, so this is a particular factor graph where if I give you a Y, finding the corresponding Z is hard because you have to run this optimization algorithm, which has an L1 and L2 term, and there's lots of work from the applied math community on how to do this efficiently. But it's still, it's not hard, but it's slow. You know, if you're going to do this on every window on an image, you're not going to have a real-time computer vision system, right? You just can't. You can't afford it. It's not hard in the computer science term of the. Say again?
What's slow here?
The slow part is the inference. So I give you a Y, find me the Z that minimizes the sum of those two factors. Okay? And you have to. You're given the W matrix. Learning the W matrix is, you know, another thing which is not that complicated if you can do the inference. Okay, so the inference, actually, the techniques that are most popular for doing this are similar to the one that David described, which you can basically split this variable in two, and there is, you know, one that only has the L2 term, and one that only has the L1 term, and there's kind of a coupling a term between the two that, you know, you with a Lagrange multiplier in front that you try to maximize. And Yes?
So, from a learning W, that task is highly non-convex, right?
It's actually not that bad in the sense that once you know Y and Z,
No, but you don't know Z, do you?
well, so it's kind of like EM, right? So what you do is,
Okay, the problem we're jointly finding Z.
jointly finding Z and W is non-convex, correct?
So,
Yes.
I'm wondering, it's a form of non-negative matrix factorization.
Yeah,
Matrix factorization.
Matrix factorization,
A
yes.
sparsity constraint
Right, right.
on Z.
Right, exactly.
How, if you do number of restarts, I'm just wondering, does the fact that you reach some local minimum on your first attempts affect your accuracy at the end of the day? Like
No.
if you did many restarts, do you get better accuracy?
No, I mean, usually, most of the local minima are equivalent, essentially. So sometimes you'll get stuck in a bad minimum where some of the basis functions will end up being random or not do anything for you. It's because maybe you don't need them. But and so if you restart, you'll get a different solution. Sometimes you'll get more of those basis functions that are actually alive. But overall, that seems to make very small difference in terms of accuracy when you stick those into a classifier at the end. Okay, so here's a way to fix this inference problem. And this is a very general idea. The idea is the following. We have a factor graph here where the inference of Z as a function of Y is painful. It's not awful, but it's painful. What we're going to do is we're going to build another factor in parallel with this one. And this one will have a structure that allows us to predict Z from Y easily. Okay? And the way we're going to build this is that we're going to build it by having a determinative function that goes this way now. And then a factor here that measures the discrepancy between the value of the variable that's being predicted and the prediction of it. Okay? So in terms of energy, it just adds another term to the energy function. So by the way, RBMs are a special case of this. Okay? But in the case of sparse coding, you can just write an energy function of this type, where you have a linear reconstruction here. We haven't changed that. And here what we have is a kind of mildly nonlinear function, or maybe a highly nonlinear function, parameterized by some set of parameters that we're going to learn. And we're going to train this to kind of minimize the prediction error for the optimal Z that we get for every training sample. So that looks like a free lunch, right? I mean, as complexity theorists in the room, which I'm not one of, you say, well, how can that possibly work? You know, I'm kind of, the problem of mapping Y to an optimal Z is a complex optimization problem, which, you know, does explaining away and stuff like that. How is it that I'm going to be able to do a very simple prediction with sort of a bounded complexity of this function and expect to get anything that's accurate? And the answer is, you're not asking this function to give you a good prediction for any possible Y. You're only asking it to give you a good prediction for the Ys that you're interested in. For example, patches from natural images. Okay? So here's an example where, you know, the worst case is really awful, but you can get away with it perhaps because you're only interested in solving the problem on the subset of the input, and that might be a particularly easy one.
So what you predict for G is actually going to be sparse vectors?
Right, so it depends what you put in this box, but the simplest thing you can do is hit the input vector with a matrix and then shrink the resulting outputs towards 0 and not allow them to cross 0. So the shrinkage function is something like this, right? Like the black curve here. And the other ones are kind of differentiable versions of it. But you can do better. So this is what you get for basis functions if you train this on handwritten characters. This is what you get. This is the learning algorithm running. So you start from random initial conditions. So each square here is a column of the WE matrix. And as things go on, this is trained on natural image patches. You get those kind of Gabor function-like oriented edge detectors. And this is what you need for vision. You know, if you were to build it by hand, that's what you would put in. Okay, but here's another idea. Came out of a former postdoc, Carol Greger, and has been picked up by a bunch of people in the applied math community. And the idea is that there is an optimal algorithm, an inference algorithm called ISTA or FISTA, which means Fast Inference Shrinkage and Thresholding Algorithm, based on this Bregman split idea. And the algorithm is like this. This is a flow graph of the algorithm. You take the y, you hit it with some matrix WE, which in the case of ISTA is the transpose of the WD matrix. Then you shrink it, and then you multiply that by a large S matrix, which happens to be the gram matrix of the columns of WD, or the identity minus some constant of that. And then you add that to the previous result you had, shrink again, and then iterate this, and this will eventually converge to the solution of the sparse coding problem. So this will find the minimum of the L1, L2 energy function. And so what Carol realized is that, well, this looks kind of like a recurrent neural net, and we could maybe unfold it for a few iterations and then train it to produce the best possible results after a finite number of iterations. Okay? So that's something like that. So unfold this kind of flow graph so that you're running 2 iterations of it now. Okay, and this is now a feed-forward system that's parameterized by this matrix and by this matrix, which is replicated in both places. And that looks like just like a neural net. You can train this with backpropagating gradient through it, so that when you plug an image patch, it will predict as well as possible the sparse code that corresponds to it. Okay. And so the Bornstein people, Bornstein, Sapiro, and I can't remember the name of the third author, Sprackman, have used this idea for doing things like source separation, and they can do real-time source separation on an iPad and things like this. Pretty cool. And my machine went to sleep. Well, that's interesting. Ha. Well, that's interesting. Okay, hang on just 1 second. Yeah, but yeah, it's something with the mouse being captured.
Quit VMware, get out of Windows.
Oh, this is not VMware. Okay. Sorry about that. Here we go. Okay, apologies. I'm not sure what happened. All right, so we can use this technique to build a convolutional net, to pre-train a convolutional net unsupervised. And so we use one of those sparse autoencoders where we show it image patches or whole images, but we have convolutional versions of this that work on whole images, where the matrices here actually implement a convolution, not just a regular matrix. And we train this thing unsupervised on, images. Once we're happy with it, we get rid of the feedback. We only keep the feed-forward function together with the absolute value. And we stick a second layer of that on top of it, train that unsupervised, get rid of the feedback, stick a classifier on top. And if you look at the functions that are implemented by this, you have a linear function, a nonlinear function, a pooling. I've kind of schematized that, but it's actually a pooling. You can stick a contrast normalization on top here. And then again, linear function, nonlinear function, pooling, and classifier. That looks very much like the architecture I was showing you earlier. But it's pre-trained unsupervised. And that works pretty well for object recognition. I'm going to skip the results that are kind of boring. This is the convolutional version of it. And you can apply this to things like pedestrian detection, and it works wonderfully. It actually beats most of the state-of-the-art. So these are curves for pedestrian detection that count the miss rate per image for a particular rate of false positive per image. So if you have one false positive per image, you know how many pedestrians are you missing. And our system, so good is kind of towards this corner. And our system is a dark blue line, so you see it's pretty much the best system of all the ones that have been tested on those data sets, except for this one here. It's a particular one. But it works really well.
So the unsupervised learning, is that done on the labeled data that's not, or is it just on the label?
It's unlabeled data, but it's not necessarily data from the same data set. It could be just natural images from other sources.
But it's still a convolution neural net.
It's a convolutional net, yeah. And it's a convolutional net that's applied convolutionally on the entire image. So it's, I can't explain quickly how that works, but that's the basic idea. You can apply this to musical genre recognition. We pretty much have results that are as good as it gets on this. But let me sort of finish with another issue I want to discuss, which is kind of more interesting for maybe in theoretical terms, which is the issue of energy-based learning, particularly for unsupervised learning. So the question is, you know, there are several frameworks for supervised learning that people have used to kind of analyze generalization properties, you know, either Bayesian approaches, the VC kind of theory, impact learning, and things like this. There's no equivalent for unsupervised learning because it's kind of ill-defined, you know, how do you define success in unsupervised learning? So really, what is the purpose of unsupervised learning? It's kind of to discover sort of mutual dependencies between variables that you're observing, right? So you're observing multiple variables, and what you'd like to know is there any dependency between them, or is there, you know, what's the distribution of the entire set of variables you're observing? And you could sort of, if you're a probabilist, you will, or if you like Bayesian methods, you'll turn this into a likelihood problem, you know, density estimation, essentially. So you have your space Y, here it's unidimensional, and you're trying to identify a density function in that space that will tell you, you know, here I'm in a region of high data density, and here I'm in a region of low data density. There's a slightly more general framework in some ways, which is sort of the energy-based view, where you write an energy function, and if that energy function has some special properties, then you can view it as a log likelihood, and you can take exponential minus this energy function, normalized by the partition function, and you will get a distribution. But there are lots of energy functions that are not normalizable, and therefore do not correspond to the log of some likelihood. Okay? But they're just equally good in terms of how they model, how they capture the dependencies of the input. So basically what you want is you want to build an energy function that the problem of unsupervised learning is you want to build some energy or contrast function that will take low values on the data and high values everywhere else, right? So here's, for example, a little functional dependency between two variables x and y, which I should have called y1, y2, and that dependency is simply that y is equal to x squared. So the training samples are the blue beads here, and what I'd like is some sort of energy function that tells me if I'm close to a blue bead or not. And in this case it's relatively simple, but there's lots of energy functions that will do the job, right? This one is just a quadratic one in the space of, for a particular x, as a function of y is quadratic. This one isn't. And the training procedure, should be designed to kind of shape this energy function in such a way that it gives you the right thing. And again, if the energy has the right properties, you can always turn this into a probability if you want to. So if you have such a energy function, you can use it for all kinds of stuff. You can use it for, say, image denoising, or deblurring. You can use it for all kinds of stuff, but you can also use it to represent data if the process of computing the function involves coming up with some latent variable that represents it. So before I go to this, the sort of probabilistic way of training those functions is simply to do maximum likelihood. So you write the probability of a given point y as this Gibbs distribution, and what you want is minimize the sum of the log of that stuff averaged over all the training set. Okay, that's maximum likelihood. What you get is a loss function of this type, which you have to average over all the entire training set. So this presumably you can minimize easily because you know the form of E, you built it. But that is much more complicated because here you have an intractable integral over the entire space of Y, which may be very large if Y is an image. So that you can't really compute. And so that's the problem of, so minimizing this will consist in pushing up the energy of all the points Y, right? So that, yes, 5 minutes, okay. And so people have come up with all kinds of methods to do this approximately. So if you compute the gradient of this loss function, the negative log likelihood loss function, you get this integral for the derivative of for the gradient of the partition function, which is essentially an expectation, where the expectation is taken over the probability that your model gives to the points. It's not the real probability. And so this will have the effect of pulling down on the energy of the training samples, and this will have the effect minimizing this because it has because it has a plus term here, will have the effect of pushing up the energy of everything else in the entire space. And the problem, of course, is that you can do this. It's just too impractical to compute this integral. So you can use variational approximations. You can use Monte Carlo methods and things like this. And there's huge literature on how you do this, at least in the supervised case. But the problem is even worse in the unsupervised case. So the solution to this problem, there are 3 solutions essentially. One is something called contrastive divergence, which is due to Hinton about 12 years ago. And the idea of contrastive divergence is very simple. You take a training sample, and you say, I want to make the energy at that point lower. So you just push down on it, tweak the parameters so that the energy goes down. And then you move away a little bit from it in a particular way. Now you get a new point, which is not the original training sample you had, but it's kind of nearby. And the way you move away from it is that you could think of it as a ball that you kick, and it's kind of rolling down the energy surface. So after a while, it's going to be away from where you started, and you're going to take this point and push up. Okay? And you can convince yourself that if you do that often enough, you push down on the points, on the training samples, and push up on the nearby points, you're going to get a groove in the energy function around the manifold of samples. And that pretty much is what you want, except that it doesn't scale very well in high dimension because you have so many points that you need to push up on. So that's not so great. Second technique is called score matching, and this one is, I'm not going to go into it, but it's not really practical for complex models. There's the denoising and contracting autoencoders proposed by Pascal Vincent and Yoshua Benjo in Montreal. And there's the sparse autoencoder technique that we proposed, and it's kind of I'm going to try to convince you in the last 2 minutes that it's actually a way of pushing up on the energy of points you don't want. So we're going back to this little autoencoder model. We're going to put some sort of constraint on Z in such a way that Z has kind of a limited capacity. And we can put this constraint by imposing sparsity, or we can put it by, in other ways, by adding noise, or by making it stochastic, or by doing all kinds of stuff. But basically, the idea of it is that you try to limit the information content that Z can contain. Okay, I'm going to actually. So this was just a slide that showed the equivalence of the fact that RBMs are a special case of encoder-decoder. But here is really the picture I want to show. So let's say you have an input space and a feature space, and you have points in both spaces here that are symbolized by those little circles. So here I have a training sample, and I'm going to train an encoder in my autoencoder to map this training sample to an equivalent point in the feature space. And if I have no constraints on the size of this feature space, if it's higher dimensional than the input in particular, then I can always reconstruct using the decoder the point that I started with. Essentially, my autoencoder now computes just an identity function. So any point anywhere can be perfectly reconstructed because I got enough capacity here to encode any input vector. But here's what I'm going to do. So it will reconstruct noisy points as well as clean points, and that's not what we want. What we want is we want to be able to reconstruct the points that are good, but we want the points that are not good, we want to not reconstruct them because we want the energy function to be high, and the energy function has a reconstruction error in it. So what we're going to do is we're going to squeeze the set of possible configurations that the feature space can take. Okay, for example, with a sparsity constraint, and now we're going to train the system so that on the training samples, the reconstruction error is minimized, and the system will have no choice but use the points that we left it. And therefore, the other ones will not be able to reconstruct because all the points in this space will have to be mapped to one of those 3 points, and those 3 points have been trained to map back to those 3 points. So, so this guy is going to get properly reconstructed, and this guy isn't because it's going to have to map to one of those 3 points. And this point maps back to a clean one. So that's an example, and denoising autoencoders are based on the same idea. So that's an example that shows that if you have an autoencoder and you squeeze the information content of the hidden layer, what you get as a result is a way of essentially pushing up on the log partition function and making sure that the reconstruction error will be high on whatever point you don't train the system on. Yeah, that's pretty much what I wanted to say for this. And so, right, yeah, I'm going to talk about structure prediction, so I'm going to stop here. Thanks. So if you train on natural image patches, you get Gabor filters, yeah.
So are these Gabor filters for natural images or for all kinds of
No,
images?
just for natural images.
Just for natural images.
If you train on color images, you get Gabor filters on the luminance components, but on the color components you get very blurry color configurations, very low frequency filters. If you train, so I have an application that I didn't show on musical genre recognition, and there the features you get are basically chords. You know, major third and.
So that's seen empirically, but it's not known like how theoretically how things come out.
Well, I mean, you know, the intuition is that the basis functions are going to be kind of parts, kind of a small number of parts that you can combine to form, the observed inputs. Which is why when you train on NNIST on the handwritten digits, the basis functions end up being really, little strokes of characters because that's the best number of small parts that you can combine a small number to reconstruct characters.
Yeah, and the second question was in the deep learning, have you tried replacing the non-linear part with the linear part and see how much of the difference?
Right. So so Kwok Lee, who is in Andrew Ng's lab at Stanford, who is working at Google, uses a very similar sparse autoencoder model. But his encoder is linear. He's got a non-linearity after that in the pooling. I don't think it's such a good idea, frankly. Michael?
So, do you have what non-linearity, any non-linearity is not?
Well, so we like to use the shrinking non-linearity because it corresponds to sparse coding, but in fact, hyperbolic tangent works just fine. Sigmoid function. Some mild non-linearity that is more or less monotonic is something that you want. You don't want something that's not monotonic because then it creates local minima of all kinds and it's a pain to optimize.
Do you have an intuition with speech recognition? Is this similar in what the different features correspond to? Seems to be natural vision, generally there's some natural interpretation.
So I haven't played with that enough myself to really tell. I think it's just. Okay, so here's a mistake that people made back in the day. So, back in fact, that was kind of the topic of one of the slides I wanted to show here, which is there's a bunch of people back in the 80s and 90s, Léon Boutou, Xavier Driancourt, and Yoshua Bengio, Patrick Hafner. Most of these guys did their PhD on speech recognition using hybrid models of neural nets and HMMs on top. And they could never beat the HMMs in sort of large vocabulary speech recognition. And the mistake was very simple. The mistake was simply that their neural nets were way too small. So if you take the sort of mixture Gaussian-based speech recognition systems of the time, they typically had a couple million parameters in them. All the centers and the means and covariance of the even diagonal covariance mostly, and the combination weights of the mixture Gaussians. The neural nets had, a few tens of thousands of parameters. And the reason for this was that computers were too slow, we didn't have much data, and we were really scared to death of overparameterization. But it turns out you just have to make the neural nets huge, at least as big in terms of number of parameters as the GMMs. and then pre-train them, unsupervised if you want multiple layers, and it just works, essentially.
Nowadays, when you use an overcomplete representation, say you don't use a convolution neural network, and you have overcomplete representation, but if you get these results filters, how overcomplete is it? So like a concrete problem.
So it's a trade-off between performance and speed. So if, typically we would get, at the first layer we would get something like 30 filters, so 30 times overcomplete.
30 filters that scan over the entire...
That's right. So you take a filter, typically it would be 9 by 9 or something like that. You would scan it over the entire input and you would have 30 of those filters.
So that's in
A
a convolutional setting.
convolutional setting.
Not a convolutional.
Or if it's not convolutional,
Yeah.
well, so for speech recognition, they're not convolutional, which is actually also a mistake. They could be convolutional in time, but the current systems that Google and Microsoft use, as far as I know, are not convolutional.
I thought you could
And it's,
you can do just as well. You can do pretty well without a convolutional.
yeah,
So.
and those are huge.
Get an idea of how overcomplete it is and the sparsity.
So it's something like the input is like a window of a few acoustic vectors. Each acoustic vector is about 50 dimensions or so. And the window is, I don't know, 5 or something like that. And then, so that gives you an idea of how many input variables there are. And I think the number of hidden units is on the order of 5 or 10,000 for the first layer. And then you repeat that multiple times. So they're huge networks with tens of millions of parameters.
But then if you have mixture chaos, it's easy to have 5 or 10,000 mixture components and you have all the different
So if you use,
frames and triphons and everything else, right? So it's
right. Well, I mean, the triphone and stuff, that just determines how many categories you have at the output. But most of the parameters are in the covariance matrices, actually. Yeah. And there you don't have that problem with neural nets. You don't have covariance matrices. Yeah.
So I'm just having a dinner outside for half an hour. Thank you.
Thank you.